Okay guys, what we're going to look at now is tables for exponential growth. And that means what we're going to be doing is looking at how we identify that a set of data is undergoing exponential growth, and then how to come up with that formula. Okay, so I've put a set of data here in the document so you can have a look at it. All right, we have a set of years, and every 2 years they've taken that sample again and they've worked out what the result is. Okay, so you can see from 1990 to 1992 is 2 years, from 92 to 94 is 2 years, from 94 to 96 is 2 years, from 96 to 98 is 2 years, and 98 to 2000 is 2 years. So we have a constant change in time, and what we want to do is we want to look at what the change is in the result. Okay, now firstly we always check to see whether it's linear. Okay, so always check first to see if we have linear change. So what's happening if it was linear? So for example, if we had a normal XY table, if we had an XY table, X, Y, and we had X is 1, X is 2, X is 3, X is 4, X is 5, and Y is, say, 8, 11, 14, 17, 18. Okay, so this is an example of a linear relationship because you can see that X is going up by a constant amount, plus 1, plus 1, plus 1. Okay, and Y is also going up by a constant amount, plus 3, plus 3, plus 3, and plus 3. This gives us a linear relationship. Okay, we're going to look at this a little bit more detail in the next video. All right, now we want to first check, as I said, whether this table is experiencing linear growth. If it was, we know already that X is going up by plus 1. Okay, plus 2, sorry. So in all these cases, X is plus 2. Okay, but what is Y? So what has Y increased by here? We can do 9.12 minus 6.75 and we get 2.37. So this is plus 2.37. The next one, 12.3 minus 9.12 gives us 3.18. So we can already see that this is not a constant change. This is not going to be linear. 16.61 minus 12.3 gives us plus 4.31. And the next one, 22.42 minus 16.61 gives us 5.81. And 30.27 minus 22.42 gives us plus 7.85. So what you can see is that not only is it not a constant change, it's not the same change each time, but that change is also increasing as we go further down the table. The change is increasing each time, it's getting larger. So every time we make another step, we make an even bigger increase. Okay, so this is not linear. All right, that's when we now look to see whether it's going to be exponential. Now there's a nice easy way to check this. To check if it's exponential growth, we just need to divide each term by the one before it. Okay, so for our first one, we're going to look at 9.12 divided by 6.75. because those are our first two values. So 9.12 divided by 6.75, and we get is approximately equal to 1.35. Okay, we might go 3 decimal places. All right, we want a pretty close answer for each one. It's never going to be quite exact. Okay, so for our second change, we're looking at 12.3 divided by 9.12. And that gives us approximately equal to 1.349. Okay, our next one is 16.61 divided by 12.3. Which gives us 1.350. Okay, our fourth one is going to be 22.42 divided by, I'll zoom out a little bit so we have a little bit better of view, 16.61. And that gives us approximately equal to 1.350 with rounding. Okay, and the last one is going to be 30.27 divided by 22.42. And that gives us approximately equal to 1.350. Okay, so what you can see is this is pretty close to being the same change each time. Okay, but instead of being plus, this was times 1.35. Okay, we have times 1.35 each time. Okay, so this is what we call exponential growth. All right, and in this case, what you have just calculated, this times 1.35, this is our growth factor. Okay, this is G. All right, so what we can now do is we can come up with our formula for this relationship. Okay, we can actually produce a formula for this so that we are able to calculate any future values. All right, so what we're going to do is we're going to come up with a formula here. All right, so we know that our general formula, for exponential growth is n equals I times g to the power of t. Okay, now in this case, we can consider that 1990 is t equals 0. So in this case, 1990 is t equals 0. So we're going to consider that to be our initial value. Okay, so we know that in our case, n equals 6.75. That is going to be our I value. Okay, we're multiplying it by the growth factor, and we already calculated that. That growth factor was 1.35 to the power of t. Okay, and we have just produced our exponential formula for this table. Okay, now if you were to take a look at the coronavirus numbers from earlier on, you might find that there was an exponential growth happening there. So maybe some of you can find some examples of exponential formulas for coronavirus. It certainly can be done in some cases, not all the time. Okay, different countries had different things going on, but yeah, it was a really nice example of what we're actually doing right now. Okay, so this is calculating with tables for exponential growth. Basically, what you're mostly going to have to do is show that you have exponential growth, come up with a formula, and then probably find some future values. So future values for this one, for example, if we wanted to know what our fx would be when t equals, in, let's say, 2010. Okay, so 2010 is 20 years after 1990. Okay, so that means we're looking at t equals 20. So in 2010, t equals 20. So then we can say n is equal to 6.75 times 1.35 to the power of 20. And that's going to be approximately equal to times 1.35 to the power of 20, 2,728.8 0.85. Okay, and that's it.